All right, let's go ahead and get started. Couple reminders. Next test is a week from today. It'll be on all of chapter 4 and section 5.1 and section 5.2, which we'll be done with by the end of Wednesday. What else? I just put up 2 new web works for 5.1 and 5.2, which are due on Thursday, Sunday. Okay. Thank you. Because of when the test is, so it's on Monday the 18th. Easter Sunday is this Sunday. I'll be out of town for most of it. I don't know if I'll be able to have like a review session some night before then. If I do, it'll probably be Thursday. So sorry, I can't be more definitive about that, but it's kind of a weird time in my semester to do that. So I'll let you know what I can do. All right, so this is our third day on section 5.1, talking about kind of getting our feet wet with integration. So the big thing we're talking about so far has been area, and specifically how to approximate the area underneath the curve using basically a bunch of rectangles. We're basically chopping this strange looking region up into many smaller, very simple shapes and trying to find the area that way. So another incarnation we can, or another kind of measurement we could take with this is finding distances. So I have an odometer on my car, it doesn't work, but I do have this information from me driving a car. So every 5 seconds it takes a speed measurement. So can I apply what we've done the last couple class periods to try to estimate a distance from this information here? How are speed and distance, or velocity and distance, how are those two things related? I think we've talked about them a lot in.
Yeah, velocity is the first derivative of distance.
So velocity is rate of change of distance, right? With respect to what?
Time.
Right. Now we're kind of using the same idea, but we're going the opposite direction, right? So something we've said, I think you even said this just now, Derek, velocity is the derivative of distance with respect to time. Now we're going the opposite way. I want to find distance. I know something about the velocity. I would like to use what I know about velocity to figure out what the distance is. So can we apply what we've done before to try to get an estimate here? Let's say our velocity is represented by that function there. Probably not accurate with this table here, but that's okay. I want to find my distance over a 30-second interval. For how many times do I know my velocity?
7 times.
I know it is 7 times, right? Let's just break it down one piece at a time. Let's say I wanted to find my distance over the first 5 seconds. How might I do that? So between time equals 0 and time equals 5, I want to figure out as close as I can my distance. What might I do there? We'll call that distance 1. It's approximately equal to what?
5 minus 0 over 21 minus 17.
5 minus 0 over 21 minus 17. What's that going to give you?
That could be good.
So yeah, I would find you a rate of change of velocity with respect to time, right? Is that what I'm trying to do? What is the rate of change of velocity with respect to time? What is that called?
Acceleration.
That's acceleration, right? So that's kind of going deeper into these rates, right? I'm not trying to do that. I'm trying to figure out. So velocity is a rate of change of distance over time, right? I know something about the rate of change of distance over time. I would like to use that to figure out what the changing distance is. So, right. So the antiderivative of my velocity is going to be the distance. I don't really have a formula or like a function, a well, like algebraically defined function here, but what do I know? So let me try to break this thing down into math speak here. So we know that velocity is equal to, I'll call it average velocity, the change in distance over change in time, right? So from there, can I say this? The change in distance is equal to whatever the average velocity is times the change in time. So this is what I'm doing this. I'm chopping, I don't know. So this curve I drew up here for my velocity, I don't really know. I mean, I know what that curve looks like at these 5-second, timestamps, but that's all I know. I'm kind of guessing at what's going on with the curve. So really what I have to do is I'm going to make rectangles out of all these intervals. Those two rectangles I drew right there, what is the base of each rectangle measure? Like what's a unit for that? Seconds. That's in seconds, right? How about the height? Keep in mind, this is a velocity over time graph. Basically, I'm trying to graph this table here.
So the height's in feet per second.
The height's in feet per second, right? So let's just find the first area. So the first area is going to be basically, speed times time. The time's easy. That's 5 seconds, right? That's how long that interval is. The velocity we have a little more control over. What should we say for the velocity here? There's no one right answer for kind of how to do this.
Oh, because it's the same thing where you can use the leftmost or the right.
Right, so I know that at the beginning of this interval, my speed was 17 feet per second. I know that at the end of the interval, my speed was 21 feet per second. But I also said that the speed was lots of things between these.
Yeah.
So, I mean, that's a bunch of different schemes I could use. So choose one. Let's just choose one and stick with it. Left side, right side, average, what do you want to do?
21.
Okay, right side. So for our first interval here, we're going to have, that speed is going to come from this calculation, 21, not meters, 21 feet per second times 5 seconds. Knowing that we could have done this a few different ways, this is not going to be a unique number. Are we okay with how we got that result? All right, so that's going to be my first distance. Let's just keep going. How would I find my next little 5 second chunk of the distance? If we're going to stay consistent with this, what speed should I use?
24.
24 feet per second. And continuing.
9 times 5.
All right. So then 32, right?
Mm-hmm.
Then 31. All right, so I'm trying to find the distance I covered over 30 seconds. Is this calculation going to do it?
Not exactly, but it gives you that.
Right, I mean, it's going to get me something. I can't really know what this is exactly, but it's going to get me something, right? So it's going to give me that right, what we call that right rewind sum from last time. Or are we convinced that this is valid?
Yeah.
So I have enough data for 30 seconds. Yeah, my intervals are all 5 seconds long, so how many of them do I need? Should need 6, right? And I think I have them. So.
So is that the stuff? Oh, okay, never mind. Yeah, erase that. Because it said D1.
Yeah, because I was going to do them one at a time, but we still did do one at a time. I just put them all in the same line.
Yeah. We're gonna estimate any shapes besides rectangles?
Not right now. I mean, here's my belief about integration. I mean, you can talk about these, geometric shapes and how to use those to approximate for so long, but really what we're working up to is not really like a geometric thing. Kind of the process to get there is based on rectangles, but the thing we're gonna end up at doesn't really have anything to do with it.
And again, that's just because the guy who theorized it had them all in rectangles.
Yeah. I mean, this is not the only way to integrate things. There are other schemes for this, but this is the most well-traveled one, probably the simplest one too. Any questions about how we found this distance? Yeah, I mean, I would love it if I had, lots and lots of time data every second, every 10th of a second.
Oh, no, I was saying, because it's like a 5 and a estimate, so.
A what?
Oh, yeah, 5 and a half.
Right. All right, any questions there? All right, that's the last thing I had for you for 5.1. And hopefully it'll be clear, if not by the end of today, then by sometime Wednesday, why I'm not gonna there are trapezoid rules and other kind of things, but at some point you got to use those to get to the end of where we're going, which is this thing called a definite integral. So that's what section 2 is all about. And again, this is the last section that you'll be responsible for the third test. And then there are only 2 sections left. Another thing I forgot to say, I put up the last quiz of the semester. It's not due for a while, but it's there if you want to look at it. I think it's due on the 29th of April. All right, so the definite integral. So this is basically the thing we've been talking about since chapter 5 began, right? I think this is actually the same curve that I showed you, the same shaded area. So how have we been finding this area? What's the thing we've been doing? Yeah, just basically splitting it up into a bunch of these vertically narrow rectangles. All right, but so far everything we've dealt with has been, these things all have, positive dimension, right? Positive time base, so positive width, positive height. How do you think we modify this if this function dipped below the x-axis, for example?
You would have to subtract stuff.
So you basically, and that's, are we okay with that? The idea of subtracting whatever area we get from those?
Anything that goes below.
Yeah, okay. So that's basically the modification we're gonna make. This probably feels intuitively wrong to say area can be a negative value, but that is kind of what we're gonna do. This Riemann sum, if we extend it negatively, we are going to wind up with these areas that are negative. So a couple things I want to highlight about this. So hopefully these A1, A2, and A5 places, hopefully those feel familiar. Those are positive. I'm going to get areas from those rectangles. Those are going to be things I add to this overall sum. But what am I doing with area 3 and area 4? Right. I'm finding those areas as I commonly would to get a positive number. Then I'm just going to pull those, subtract those from my sum. What do we notice about these intervals?
So are you trying to find the area of A1 to 5 or all of them?
Look at that sum. What is that sum giving you down at the bottom?
1 to 5.
It's kind of the area of all of them, right? Treating the ones that the rectangles below the x-axis as negative. But that is the sum of, I'll just ask again, that's the sum of how many rectangles? 5. Some of them are negative. Just a couple of reminders of notation here. What does the thing below the sigma represent?
Where you start counting?
Where you start, and this one is where you finish, right? That one is usually variable in this case. We can just kind of work up to it. Why do I have a star over x sub I? Or maybe I should back up a step further. What is the I even there for?
Start counting X1.
What's that?
Start counting at X1.
When you say start counting, yeah, basically,
Right there, first rectangle.
right. So you're counting from whatever the index is to begin, you're counting up by ones to whatever the terminal index is. So I want to find area 1. How do I find an area 1? How do you find an area of an rectangle? Width times height, right? So the width is going to be delta, right? So that delta x is basically what the change is in x from here to here. And what is f of x of I? F of x sub I star. First of all, what is x sub I star? Did I talk about why I have that weird star thing?
We touched on it last week.
I thought I did. How am I choosing my x values on these rectangles? Yeah, so yeah, where it intersects with the graph, but why did I, like, for example, why did I choose this place or this? Couldn't I have chosen this point and raised this rectangle up a little bit? I could have, right?
Yeah.
I definitely could have chosen anything. So basically what the star represents is I have to choose an x value from an interval. There's no rules for how I choose. I can choose wherever I want. And there doesn't seem to be any kind of reasoning behind the points that are chosen here.
Gotcha, so yes, it is because whatever you feel.
You gotta take one. You have a continuous function, you gotta take an x value and figure out what the function, what the y value is that goes with it, but doesn't matter what that is. So again,
As long as it's in the area of the.
yeah. Like for area 2, it wouldn't make any sense for me to choose a point like down here.
Yeah.
Any questions about the modification we made here? Basically now we're allowing for these signed areas. Areas can be positive or negative. And we're just gonna add them all up and get a value. Solomon?
So like, I'm still a little shook on how an area could be like, an area is still just an amount of space. How can an amount of space be negative?
So again, I think the way this is devised, and I think on purpose, this is not saying that, so I don't think this is saying that A3 is negative. This is saying that A3 is positive, and whatever that is, I'm subtracting that.
From the overall.
Right. It's like let's say you have a plot of land, and I carve a piece of that out and take it. Like, that's mine now. I'm not saying that land is negative, I just took it from you. As far as you're concerned, you lost it. The same kind of thing here. That area exists,
So you're losing space.
it's cutting into, like it's taking away from whatever this total is. That make sense? Yeah. Yeah, I understand the intuitive like conflict that area cannot be a negative thing. All right, so a little more thing about, let's put some formality behind Riemann summations. So you have an interval, AB. We saw this with the parabola, we had an interval 0, 1. But in general, if you have a closed interval, we can partition it into many smaller subintervals. As many as I want, really. In each subinterval, a sample point's defined. We call those sample points, basically those are your xi stars. And the reason we call it a sample point is because I'm going to plug those x values into whatever the function is and get a y value out of that. For each subinterval, you're multiplying the length. The sample point that I'm talking about here is the y value. So you're multiplying whatever the length of that interval is by whatever the f of x sub I is. So each one of these is like finding the area of a rectangle, right? And then I just take all those products and add them together. And if I do that a bunch of times, I'm going to get a estimate for an area that probably will be wrong, right? So the whole idea of a definite integral is to create so many rectangles that we are no longer wrong. We're trying to get something exact. So last slide I showed you a summation notation, a sigma notation with 5 rectangles. This one is really any number that I want, right? Realizing they're all going to fit this pattern, so I can just put the ellipses in place a lot. So again, I'm kind of trying to warm you up to the big new ad today. Hopefully this looks somewhat familiar, but if something's throwing you, ask me questions. Isabel.
Could you just explain the conformal equation?
This one here?
Yeah, because we have F and X, which I'm guessing is like a Y.
Yeah.
Attribute percent. Yeah.
Yeah, so. Yeah, on the left-hand side here, root, and I think
That's like the sum of.
the new thing at this, so the power and the way this is capital sigma notation works is, so I'm starting counting my indices from 1 up to whatever n is, right? So that means the first term is gonna look like f of x1 times delta x1,
And delta X1 comes from.
however wide this is. And that's another thing I want to put on the slide, look at all these widths are all different,
So the width could be
the
different.
width can be different on all of them.
Does the info and then my height.
So that's kind of a wild west nature, because I could make the widths of all these things different. I could choose any point on the interval however I want, but it doesn't have to be consistent for in any way.
Even within the function, doesn't it?
No, I could, this one's near the left end of the interval, this one's near the right, this one's kind of center. Like I said, maybe there's no reason why you would want to do that, but you can. That's how this Riemann sum is basically how it was theorized. Pick an x value on the interval, find the y value that goes with it, and then multiply the length of the width and the height. And I think to get back to this, the left-hand side versus the right-hand side of this, basically the left-hand side is all this stuff condensed. This has eyes in it to generalize all this stuff. So the eyes are not going to show up here. Basically, this is, I'm gonna find how many rectangles, however many that indicates. I'm gonna add them all together like that.
Use the notation I rather than N.
Yeah, so, and to remind you, I have two letters going on here, right? I and N.
N is just kind of like.
Which ones are variables?
I?
The I is a variable, is N variable? No. The N, so the N is telling you how many times am I gonna multiply, how many things am I gonna add together? But really, even though we don't know what this is, we treat it like a constant. The I is a variable because, all right, I start with I being 1, and then I do this. Then I make I equal 2, then I do this. And I do that over and over, and I add 1.
Up to whatever that.
Up to whatever N is. Yep. Yeah, I mean, I know that's brand new notation, so let's take it as slow as we have to. I'm guessing that nobody's ever seen that capital sigma thing before, like last week. Yeah, before last week. Yeah. I've shown it to you, but before that it was brand new. So the thing we're working up to is this thing called a definite integral, which is really the limit of the thing that we've been talking about. So ignore the thing on the left for now. The thing on the right's more familiar, right? So that sigma notation is the sum of all those rectangles, or that's the sum of all the areas of rectangles, right? This thing here? Y value times X values, add a bunch of areas of rectangles. This thing here, what does the delta xi stand for?
Change in X over.
That's the width of the intervals, right? Now, I want the maximum width of all those intervals to get very, very, very close to 0, right? If I have widths of rectangles being very, very close to 0, how many rectangles am I working up toward? An infinite number, right? Yeah. And when I limit that process, that's when I go from Greek capital S, because they figured out this sum, or they developed a notation, to German capital S, because Riemann is German and he figured out how to make all this stuff work. So that integral symbol, basically these two things are equivalent. The Riemann sum is kind of it's the finite version of this process. I have a whole lot of rectangles, and as I start getting infinitely many of them, I transform that sigma sum into this infinite integral. And I kind of hid it from you, but we've done a couple of these because didn't we do an example with the problem where we made infinitely many rectangles? So we did one of these. I just didn't show you the notation. But that's how closely related these things are. But note how many parameters I have to deal with for that sigma notation. I have to know how wide my intervals are. I have to add a bunch of things up. So the integral is just, all right, how wide is the interval? And what is the function, right?
But capital sigma and German S are both mean the sum of. And the.
Yeah, but the difference is how many things.
Okay.
The one on the right is the sum of finitely many things.
Okay.
The integral is by definition the sum of infinitely many things.
So the
You
one
can
we
tell the fact that this is a number, right?
Yeah,
So that can't be infinite.
but.
I can take, I mean, it's just like with limits, you're investigating what happens as you approach infinity, even though infinity is not a thing we can
Mhm.
attain, right?
But like, what is B's? B's just the endpoint value?
Oh, so A and B are the ends of an interval. So
So that would be like the.
this doesn't even indicate that.
But it indicates that you start at 1 and go to n, right? Isn't that the start and end points of the interval?
No, let me give you a concrete example here. So we did the parabola right on 0, 1.
Yeah.
So that looks like this roughly. And we did it with lots of rectangles, right?
Mhm.
So here's 1, here's 0. And I remember when we did this in class Friday, how did the ends of that interval like show up in our calculation? How do we find delta x? Okay, so the delta x is the width of one, or for us, it was the width of one interval because we made them all the same width, right? And the way we did that was like this. D minus A over N, which was equal to 1 minus 0 over N, right? So when we were doing the sigma notation, the AB closed interval was kind of baked into the delta x. But there's no delta x in the interval
On the left side.
on the left hand side. Because what is the change in x for all the subintervals in this thing here? It's going to be equal to whatever I told you I was limiting it for, right?
Oh.
There is no width to speak of on this thing. The width has been taken to 0. Isabel?
Do you guys, is that something like different?
Or is that the distance?
It's like different.
It's a small change in x, but it's basically,
Oh, okay.
it's not a coincidence that we have delta x on the right and dx on the left. This right here means there's some separation.
So because
This means that it's been limited to 0.
Oh, okay.
We're looking at a limit. So basically, kind of like we were talking about limits and derivatives, the right-hand side of this involves no calculus at all, the left-hand side does. Because the thing that basically unites calculus with everything you did prior to that is the idea of a limit. So that the sum in and of itself does not have anything to do with limits or calculus. I have more bullets on here. So if that limit exists, which just kind of looking forward, the only kinds of functions we're going to be talking about with integrals are going to be continuous ones. Continuous functions are always integrable. Their integrals exist. So theorem, if f is continuous or has finitely many jump discontinuities, then that will be an integral. We're not going to deal this semester with functions that have jump discontinuities, which is going to deal with continuous ones.
Is that something you do in Calc 2? Which I was-
You might. It's actually not that difficult to deal with. It's just, yeah. And once we take some integrals, I'll show you why it's not that big a deal. It's just not a big deal right now. So I wanted to express this limit. So that's a sigma notation, right? I want to basically, my delta x is however wide each of my intervals are, right? From 1 to n. Let's build this up a little bit. What is my closed interval that I'm trying to find this area on? 1 to 5, right? What does this thing look like? sort of looks like this. I'm going to integrate from 1 to 5. So really, in the language of area, I'm trying to find this area here, right? So the sigma is going to be dealing with that in terms of rectangles, right? How would I find my delta x for that segmentation up there?
How many rectangles you decide to have?
Let's say I have n, I want to keep it general. I want to have n rectangles. How wide is each one going to be? How wide is the whole interval? It'd be, right? Which is how wide? 4 over n, right? So if it's a closed interval from 1 to 5, the whole thing is 4 units wide. If I'm going to divide that evenly into n rectangles, each one's going to be 4 over n wide. But what do I want to do with n for that summation?
It's going towards infinity.
I want to make infinitely many rectangles, right? So if I take this summation of function value, so basically what this is equal to, delta x is my change, and that's my width of my intervals, right? This thing right here is what? What's this? What is this standing in for?
For that f of x.
Right. This is my f of
That's
x I star. That's my function, right? So if I'm going to take an infinite number of rectangles and find all their areas and limit it that way, then what I'm really looking at is this: the definite integral from a to b of the function with respect to x. What are a and b in this case? 1 and 5. What's f of x?
1 plus 3 over x.
Almost 1 plus 3 over x. Why am I dropping the I?
Because it's no longer.
Right. I'm no longer dealing with this summation of some number of rectangles.
Now
Just
going to the
instead of having to think about the function as being this partitioned up thing, now it's just now I'm just looking at the function. So this is not an integral we can do right now. Or actually, we probably could. But right now, I just want to show you how these two things are related. So kind of just putting the last few days in perspective, we started by looking at the sum of some number of rectangles, a number we can actually, as humans, get our hands on. Now we're trying to see what happens as we limit that as making infinitely many rectangles, and that's what gives rise to this new thing, this integral.
And that's the express integral of that.
Yeah.
function.
So here's, and going back to my graph here, the rectangles were how we did it last week, right? But now, after I've taught you how to take integrals, that will allow you to find this area exactly. Not estimated, it'll be the number. Any questions so far?
So it wouldn't be like, because like when you approach a limit, it's not an exact number, but for an integral,
Yeah, it
it's
is.
an exact area.
When you approach a limit, you're approaching a number.
But like you don't actually touch the number. It's a limit as you get to the number, isn't it? Like it's not.
Yeah, but that number is still that whatever number you find, like for example, what's an easy one we can talk about quickly? The limit as n approaches infinity of 1 over n is equal to what? 0. Does there exist a value of n that makes 1 over n equal to 0? No, I will never reach 0, right? The limit is exactly 0. Because I can get if I can get as close, so 0 is the number I can get as close to as I want, right?
Can't touch it.
Doesn't matter, I can get as close, that's what the limit is about. I can get as close to it as, you give me your smallest number you can think of, and I can deliver the value, I can give you a value of n that puts me within that range. So yeah, for limits, I'm gonna have to retain. So even though I can't get to zero with that like expression, with that equation, the limit is exactly zero. Same kind of thing with an integral. We as humans can't deal with an infinite number of rectangles, but we can examine what would happen if we were able to look at that one. So we can get these areas when they exist, we can get them exactly. So, some important things to look at here. One of these I gave you for free last week, right?
Second.
Yeah, when you add all the square numbers together, or however many you want, you'll get this sum here. This one I can briefly try to prove to you. So that first one, what am I adding together? Let's replace n with 4. Then what am I really adding together? Yeah, so 1 plus 2 plus 3 plus 4 plus blah, 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 plus n, right? What if I were to add the first term and the last term? What would that be? Maybe I'll make this more clear. What's the sum of the first term and the last term? No, I was sorry, I'm going to n, not 4. 1 plus n, right?
Right.
What's the, so what's, now work inside from both directions. What's the sum of the second term and the second to last term? It would be 2 plus n minus 1, right? So isn't that also 1 plus n? How many pairs of n plus 1 am I going to add together?
Whatever n is.
Not quite whatever n is, right? Because I'm taking them in pairs. So basically it would be, I'm going to have 1 plus n, and I'm going to have n over 2 pairs, right? Which is basically what this is. So that's why that sum is the way it is. This one would take me longer to convince you of. This one I'm not even sure I see. So when we have to find areas, these are things that I'll give you for free. I don't expect you to remember those. But how about this one? If I sum up this many constant c's, what's my sum going to be? Just equal to the constant? Let's do that. Let's start adding things up. When I is equal to 1, what's the first number I'm going to add to something? What's the variable for these summations? It's not n.
It's I.
It's I, right? Does I appear in like inside the sum notation, inside like the sum ends here?
And the constant amount of direction.
Right, but
Well, yeah, we're not calling it.
so n is like a constant, I is a variable. Does our variable show up inside that formula at all?
No.
No, so the first thing I'm going to add up is c. And then what's the second term? C. Basically, all I'm doing is adding c to it. I'm just adding c a bunch of times, right? Would it be more clear if I put a number in here? Pick your favorite number. 5? Somebody else pick their favorite number.
2.
Okay, I'm flipping them. That's kind of boring. All right, so what's this summation going to look like?
2, 4, 6, 8. Isn't it just going to be
Which-
c to the power n?
It's not to the power of. So we're a sum. This sigma notation is all about sums.
2 times that.
2 plus 2 plus 2 plus 2 plus 2, right? So it just takes whatever the constant is and just adds that many of them together, right? So if I generalize that, what is that summation of they're going to equal?
C times n.
Cn. Yep. I'm taking a bunch of c's and I'm adding them together. How many times? N times. All right, this one's a little different. That's when I actually do have variable stuff going on. but I'm multiplying each one of those variable terms by some constant, right? So in that case, I can just say that this equality is always going to hold. That's what I meant to say. It's equal to C times that summation. Basically, you can factor out the constant. Just like I could have factored out 2 of all these things, right? 2 times 5, just like we got. And the last one, a Z.
No, that's the summation.
That's me trying to make a sigma with no room. This one here, this sort of acts the way you think it would, probably. Sum and difference. How does sum and differences work with derivatives
Take the derivative
of each one, right? So very much for the same reasons, which we'll get to later. We can handle this way too. As long as I can do it. There we go. So just like with derivatives, you can handle them term-wise when they're added or subtracted. We're going to do that with integrals when we get there too. How are we doing? Okay at best?
No, this is not that.
Okay is okay. You learned this thing 3 minutes ago. It'd be weird if you had it nailed. So I want to approximate this definite integral using right-Riemann sums with 6 rectangles. So what does this thing mean?
We start at 0 and go up to 5.
What do you mean by start at 0 going to 5?
Our first x value that we care about here is 0, and we go to x equals 5.
Okay,
And then taking 6.
so let me stop there. So we're starting at x equals 0, we're going to x equals 5. Not to scale, this might hurt your eyes, but so this is the function that I'm looking at, right? And that's one distinction I want to make here is that, yeah, the 0 and 5 correspond to whatever the interval is. They do not correspond to like delta x or, you know, anything there. What's the graph I drew up there? What function is that? Was that?
Well, this is like the one like x
That's-
equals y.
Yeah. That's, yeah, f of x equals x. Is it clear why that's the function I graphed?
Yeah, that's the function.
Okay. I'm just making sure. This is brand new stuff. So yeah, that's the area I'm trying to figure out. I mean, really, geometry could get you where you want to go here. But let's stick with the integral. So I want to use a Riemann sum. Why did I choose 6? Doesn't make any sense. Let's make it 5 rectangles. So if I want to approximate that sum, now we're talking Riemann summation, right? So we're talking the other language. Fill in this summation notation for me.
For I equals 0. That I equals 0, I equals 1 in this case.
Actually, it doesn't matter. You call it. What do you want to do? I equals 1 to what?
2, 5.
If you called it I equals 0, what would I have to put up top? Well, that would be no rectangles, right? So here's the thing. Here's what I mandated of you. 5 rectangles, right? So your summation just has to bear that out somehow. Either you count from 0 to 4, or you count from 1 to 5, or -2 to 3.
That's just less than one right answer, right?
Yeah, based not left endpoint, right endpoint. Maybe that's why I chose 6 rectangles. So I wasn't fighting over different meanings of the number 5. So if we do 6 rectangles, how wide is each rectangle going to be? 5 divided by 6, right? So delta x is equal to b minus a over n, which is equal to 5/6, right? And keep in mind what we're doing here to approximate an integral, and we're kind of translating back and forth between sigma notation and integral notation. Basically, what I'm looking at is this: f of xi star times delta x. Delta x is going to be a constant thing, right? From interval to interval. How do I find my f sub xi's? Let's do this first. How do I find x sub 1 or x sub 2? I want to write Riemann sum, so what's my first x value going to be?
1.
I don't agree with 1. Not 0, because that would be if I was using the left endpoints.
Oh,
Right.
So here's my first rectangle. How far across is that first rectangle?
5, 6.
5, 6. How do you know that?
That's the change in x.
Right, so it's the left end of the whole interval plus whatever the change in x is, right? What would the next, so this was 5, 6. What's x2? How far across is that rectangle?
5, 6.
No, I mean, this is not for, so they're all gonna be 5, 6 apart from each other, right?
No.
So, but what is the actual x value there?
Oh, there's
You went to the right 5, 6. How much further are you gonna go to the right?
another 5, 6, but not like another 5, 6.
Another 5, 6, so that'd be,
It's totally 5, 6.
No, it's gonna be.
so
It's gonna be 10 6.
there you go. And maybe I wasn't being clear. In fact, I'm sure I wasn't, but I'm looking for the actual x values, right? So 5, 6, and hopefully it becomes clear later why I'm doing this, but 15, 6, 20, and so on, right? So can I generalize this? Can I generalize to xi star? Based on the first 4 entries here. If I is equal to 1, x sub I is 5, 6. If I is equal to 2, then it's 10 over 6. Can I come up with like a formula or a function that relates I to x sub I?
I times 5, 6.
I times 5, 6. Does that fit for these 4? Looks like it does. So x sub I star is going to be 5, 6 I, which means f of xi star will be what? That's the y value, but do I know what y is equal to for this function?
2 over x.
So what would f of xi star be?
It's just, it would not be 5, 6.
Okay, so maybe I should stop here. No, not for the day, just to debrief. So what are we doing here? Basically, what I'm trying to do is, by writing out the first few terms, trying to come up with like a formula for xi star, right? A function that goes from I to x. Once I have that, I can plug all, basically, once I can do that, I have all of my x values, right? I have x that goes to all of my I values. How do I get f of x sub I star equals 5, 6 I? Why are they the same?
The function is just x.
Yeah, it's this identity function, right? F of x equals x. So now what I have is basically all the specifics for this function. F of xi star is 5, 6 I. Delta x is 5, 6, right? So now can I add these, can I write down all these rectangles or write down all these values and get a sum? When I equals 1, I get, actually, can I do this? I told you that I can factor out constants, right? So can I do this? Factor out this 5, 6? And then I can factor out, actually, you know what? Can I do this? 25 over 36. And now I'm just summing up I. Is that legal? Is 5/6 a constant?
Yes.
Is the other 5/6 a constant?
One was a constant, one was a.
No, they're both constants, right? What's the variable?
I.
So I have to leave that one inside the summation, right? But because of that, I can now think of this as 25 over 36 times that sum. What is the sum from 1 to 6 of I? I'm just gonna write this down and let you calculate it, but I equals 1, summing up, so the summation from I equals 1 to 6 of I, what's that gonna look like? When I equals 1, what term am I gonna get out of that? So we're just the summation notation. Remember, I factored out all the other stuff, right? So now the summation notation, all it does is, so I counts from 1, 2, 3, 4, 5, 6, right? So it's gonna, the sum's gonna be 1 plus 2 plus 3 plus 4 plus 5 plus 6. So I think there's still some confusion, and I'm not surprised by it, but how to read this thing, right? So basically what the sigma means is I'm gonna add up some stuff. Now you gotta figure out what you're gonna add together. When I equals 1, it's gonna sound dumb, but I have a reason for asking it this way. When I equals 1, what does I equal? So that's the first term, right? Okay, continuing, when I equals 2, right? And how do I know to stop here and put parentheses here?
Because that's the top. of the
I told basically, I created a loop for you and told you how many times to run. Does that make sense? Okay, so we'll keep picking at that on Wednesday. I'll see you then. Yeah,
You chose the right points. Is that because that's what falls in the area?
that's that's what I told you to do.
Okay.
That is the only rationale. I could have said choose the left end points.
But then would you have to, would you have to subtract the area